Hello there. Welcome to Merrivet Education Center, and this is Science with Master Rick. How do we define force? Do we believe that we know more about this concept than we really do? Whatever your answer may be, just join me in this exciting journey of discovery. The classical definition of force shows that an object may at any given moment exist in either two states. Number one, the state of rest or the state of motion. The definition further said that when force is applied on an object, which is in constant and in straight motion, will cause to change its motion. Now, this change may either slow it down, speed it up, or change the direction of its motion. An object in the state of rest may also be affected by the application of force as it may also undergo motion. Now, simplifying our definition of force would say that it is an external stimulus of either pushing or pulling an object, causing it to move. An object at rest, therefore, may stay on that state forever if no external stimulus or a force, specifically an unbalanced force, interacts with it, causing it to move. Force is always associated with motion. Why? Because if we apply a certain amount of force on an object, such that the applied force is stronger than the counter force, which is friction or frictional force, then the object should move. Now, friction is the force resisting the relative motion of solid surfaces, fluid layers, and material elements sliding against each other. Force then produces motion, and it affects, number one, any object traveling at a constant speed on a linear path by either slowing it down or speeding it up or changing its direction. Number two, any object at rest. Now, the two postulates can then be lumped together, forming the basis of the first law of motion as stated.
The force is related to and associated with motion, so it goes then that force is both a scalar and a vector quantity. It means that the value of force, which is expressed in newtons, is a derivative of the product of the object's mass to its acceleration. Now, another way of putting it is that force is both magnitude and direction. Magnitude means the measurement of the size of the force that was exerted on the object or the body. Direction means the direction with which the object or the body will move in relation to the resultant force exerted. A force acting on an object may be concurrent or non-concurrent. We say forces acting on a body are concurrent if they are directed towards the same direction on the same plane. Non-concurrent, however, if the forces acting are not directed to the same direction on the same plane. To better understand force dynamics, in physics and in engineering, we use the free body diagram. The free body diagram is just a graphical illustration of the forces that are acting on a body. We've learned that even if an object is at rest, it is still subjected to several forces. Let's take a look at our box example in this frame. Let us say our box is just resting on the floor and no external force is acting on it to cause it to move in any direction. Are we correct to assume that there are no external forces at work here? No, we are not. But you know better, right? Because you know that even if it is at rest, it is still subjected to two forces. We can better illustrate this by drawing a free body diagram. The two forces that are acting on our static box are directed upwards and downwards. We illustrate this by indicating the one directed upward as the normal force or F norm, which is just the counterforce exerted by the floor on the box by virtue of its weight, or Fg. Any lateral forces, whether parallel or not, applied on either direction, left or right, would constitute the applied force, or F Now, if there are no external applied forces coming from the reverse direction, our reverse force would then just be friction, or F friction.
Now, Newton's second law of motion states that when a constant force acts on a body, it causes it to accelerate, such as to change its velocity at a constant rate. Now, in the simplest case, a force applied to an object or to a body at rest causes it to accelerate in the direction of the force.
Oftentimes, we know the magnitude and the direction of the forces that act on an object, but we still need to find the resultant force thereof. Experiments show that when an object is subject to several forces like F1, F2, and so on and so forth, the resultant force R is the vector sum of those forces. Take note that this is not a mere sum of the magnitudes of the forces, but the sum of the forces taken as vectors, which is more involved because vectors have both a magnitude and a direction that we need to consider when doing the sum. This can be simplified with the mathematical expression as the summation of all forces F acting on a given body. If we know the mass m of an object and the acceleration a produced by the forces that act on it, we can find the resultant force using Newton's second law of motion. Indeed, according to Newton's second law, the force F that alone produces the acceleration a on an object of mass m is F is equal to m times a, which indicates that the resultant force has the same direction as the acceleration and a magnitude equal to the product of the mass and its acceleration. So what do we know so far about forces? Number one, we know that force is a vector quantity, that it has both direction of motion relative to the degree of the amount of force exerted. Number two, that force should and must accelerate an object from a state of rest to a state of motion, or alter the speed or course heading of an object, body, or projectile traveling in constant linear motion. Otherwise, the net force acting on the said body would be zero. Number three, that a net force or resultant force is the sum of all forces acting on a body. So far, all of our examples and all of the things that we have learned so far pertains to forces that are unbalanced. And what are unbalanced forces? Now think of it this way. When an object is at rest, it is wrong to say that since the net force is zero, because there's no motion nor acceleration, there are no forces acting on that object. Yes, there are. Gravitational force for one, and the supportive force that is exerted by the surface where it is resting onto the static object. Now, since all forces are equal in magnitude, the resultant force is zero. Same goes for objects traveling in constant and straight motion. Therefore, unbalanced forces are forces that must be greater than the other forces present and exerting on an object to cause it to move.
Now, here is an example of two unbalanced forces with different magnitudes acting on this wooden box. Now, since both forces are acting on this wooden box are coming from two opposite directions, can we still predict the direction of motion of this object? The answer is yes. Definitely yes. All you have to do is to determine all forces acting on this static object, then group together all forces coming from the same direction, add them up, and whatever the sums are, subtract them from each other. Then you will have your resultant force. Lastly, all Newtonian laws of motion are based on unbalanced forces acting on objects that are either at rest or in constant state of motion. They are also the foundation of our modern understanding of the definition of force, the dynamic of forces, and how forces function. Now, here is the classical mechanics mathematical definition of force, whereby force, denoted by the symbol capital F, will cause an object with mass m to accelerate. Acceleration in this case is defined as the rate of change of velocity over time. But what then is velocity? Velocity is just speed, like 120 kilometers per hour or 85 kilometers per hour, but with the added element of direction. For speed, you would say 56 kilometers per hour. For velocity, you would say 56 kilometers per hour headed north. Here, you include the direction of travel. In our modern understanding of forces based on the mathematical laws of motion formulated by Sir Isaac Newton, a push or pull, which we understand to constitute force, must in effect cause any object to accelerate, thereby displacing. Why is that so? Simple. If you recall our definition of balanced forces, we found out that balanced forces are forces that are equal in size but opposite in direction. Balanced forces will not change the motion of an object. This means that the object will not accelerate. When balanced forces are acting on an object, it has the same effect as if there was no force at all, because they cancel out each other. Remember, only unbalanced forces will change the motion of an object and cause an object to accelerate. Therefore, in classical Newtonian physics, a net force accelerates an object with certain mass to the direction in which the net force is directed. And that ends our topic on resultant forces. And remember, always, science is cool.